Hello everyone, welcome to this video on the factory design pattern in Python. The factory pattern is a powerful creational design pattern that helps you manage object creation in a flexible and scalable way. Instead of directly instantiating objects, the factory handles the logic of which class to instantiate based on input or conditions. This makes your code more maintainable, less coupled, and easier to extend as your application grows. In this video, we'll break down the concept, explain why it's useful, and walk through coding examples to see it in action. 1. Introduction. The factory design pattern is a method of creating objects where the exact type of object to be created is not determined by the client code, but by a separate factory class. This pattern helps separate the logic of object creation from the main code, making the system more modular. By using a factory, you can ensure that the creation process is flexible and allows the system to grow easily. Instead of directly calling new to create objects, the factory handles this task, leading to cleaner, more maintainable code. This approach also supports loose coupling, meaning different parts of the system don't need to know the details of object creation, making the overall structure more flexible and adaptable. Key characteristics. The factory design pattern has several key characteristics that make it effective for managing object creation. First, it provides an object creation interface which standardizes how objects are created without specifying the exact class. This allows the code to remain flexible and easily extendable. Another important feature is loose coupling. By separating the object creation logic from the client code, it ensures that different components of the system can work independently, leading to a more modular and maintainable system. Lastly, subclass delegation allows specific subclasses to decide which concrete object should be instantiated, making it easy to introduce new types without altering existing code. This promotes scalability and adheres to the open clause principle where the system can be extended without modification to core logic. 2. What is the factory design pattern? The factory design pattern focuses on creating objects in a flexible and scalable way without directly specifying their class. Instead of the client code being responsible for creating objects, it delegates that task to a factory class. This factory class decides which object to create based on certain conditions or inputs provided. This pattern hides the complexity of object creation, allowing the client to simply request an object without worrying about its construction. It's especially useful when there are multiple possible classes to instantiate as the factory makes the decision dynamically. This approach leads to cleaner, more maintainable code. Real world analogy. Imagine walking into a car factory where you can order a specific model of car without needing to know how it's built or what materials are used. You simply make a request and the factory takes care of the assembly and delivery. Similarly, in software, the factory design pattern works in the same way. Instead of client code worrying about how objects are created, a factory clearly steps in, handles the object creation, and ensures that the right type of object is built based on the client's request. This approach keeps things simple and organized, allowing the client to focus on what they need rather than how it's done. 3. Why use the factory design pattern? The factory design pattern is ideal for situations where the exact type of object you need is decided while the program is running. Instead of hard coding object creation, which can make classes tightly connected and difficult to manage, the factory pattern assigns this task to a separate factory class. This approach ensures that your code remains flexible and scalable, allowing for easy updates or new object types without major changes. By centralizing object creation, the factory pattern also keeps behavior consistent and makes it easier to manage dependencies, especially in complex applications. 4. How to implement the factory design pattern in Python? To implement the factory design pattern in Python, you need to create a factory class or method that handles object creation. Instead of directly instantiating objects in your client code, you pass parameters or conditions to the factory class, which determines the correct object to return. This way, the object creation logic is separated from the client code, making it more organized and adaptable. The factory checks the input and decides which class to instantiate, allowing easy changes or extensions without altering the core logic. Step-by-step implementation. In this example, we implement the factory method design pattern, which provides a way to create objects without specifying the exact flightless object that will be created. As seen in the earlier responses, design patterns like singleton and factory method are commonly used to handle object creation and resources management in a structured way. Here, the product factory class is responsible for creating different types of products, e.g., product A and product B, depending on the input provided by the user. This decouples the object creation process from the client code, making the system more flexible and extensible. We define an abstract base class product which acts as a blueprint for all product types. Both product and product are subclasses of product, each implementing the operation method. In product, the operation method returns the string product A, while in product B, it runs product B. These subclasses represent specific product types. The product factory class contains a static method create underscore product which acts as the factory method. It accepts a product underscore type parameter that specifies which type of product to create. If the input is A, it creates and returns an instance of product A. Similarly, if the input is B, it returns an instance of product B. If an unknown product type is provided, the method raises a value error, ensuring that only valid product types can be created. In the usage example, when product factory dot create underscore product A is called, the factory creates an instance of product A, and calling product dot operation returns product A. This pattern simplifies the object creation process by centralizing it within the factory class. It allows the client code to remain unaware of the specific classes involved in the product creation, promoting flexibility. If a new product type, e.g., product C, is added, the only modification required is an update to the product factory method while the client code remains unchanged. By using the factory method design pattern, we achieve loose coupling between the client code and the specific product classes. This approach is particularly useful in scenarios where the type of object that needs to be created can change dynamically at runtime, making it easier to manage and extend the system without impacting the client code. 5. Real world use case factory pattern in action. 1. Vehicle manufacturing system. In a vehicle manufacturing system, different types of vehicles like cars, trucks, and bikes need to be built based on specific needs. Instead of hard coding the logic for each type of vehicle, the factor pattern allows dynamic creation of vehicle objects. The system can easily produce the required vehicle type by simply passing the specification to the factory, which then creates the appropriate vehicle without modifying the core code. This approach ensures flexibility and scalability as new vehicle types can be added without affecting the existing system. Why factory pattern? The factory pattern offers a flexible and scalable approach to managing object creation, especially when dealing with different vehicle types. And by it keeps the object creation logic separate from the client code, which means the system can easily extend to support new vehicle types like bus or van without modifying the core logic. This promotes loose coupling, making the code more maintainable and adaptable. The pattern allows the dynamic creation of objects based on user inputs or configurations, ensuring the system can efficiently handle changing requirements without altering existing code. Expanded use case. Imagine an online vehicle ordering system where users can select different types of vehicles like cars, trucks, or bikes, each with unique features. The factory pattern makes it simple to create these vehicle objects based on the user's input. If a new vehicle type, such as an electric car, is introduced, the system can be updated with minimal changes. This is because the factory pattern easily extends the object creation logic, allowing new vehicle types to be added without altering the existing code, making the system more flexible and adaptable to future changes. Practical implementation. In this example, we implement the factory design pattern to create different types of vehicles, car, truck, and bike without the client code being aware of the specific classes involved in the instantiation process. As explained earlier, the factory pattern allows us to centralize object creation logic in a dedicated class, in this case, the vehicle factory. This pattern provides flexibility by decoupling the client code from the specifics of the object creation process, making it easier to extend the system by adding new vehicle types in the future. The base class vehicle defines a method info that is meant to be overridden by subclasses car, truck, and bike. Each subclass provides its own implementation of the info method, returning a string specific to the type of vehicle. For example, the car class returns this is a car, while the truck class returns this is a truck. This demonstrates the principle of polymorphism, where different subclasses can have distinct implementations of the same method. The vehicle factory class contains the static method get underscore vehicle which serves as the factory method. This method takes a string input vehicle underscore type and based on this input returns an instance of the corresponding vehicle class. If the input is car, it returns a car object. If truck, it returns a truck object, and if bike, it returns a bike object. If the input does not match any known vehicle type, the method returns none, allowing the client code to handle invalid inputs gracefully. In the usage example, the program prompts the user to input a vehicle type and then calls the vehicle factory.get underscore vehicle method to create the corresponding vehicle object. The client code doesn't need to know the specifics of how the vehicle object is created, it simply interacts with the returned object via the info method. If the input is valid, the vehicle's information is printed, otherwise, the program informs the user that the input was invalid. This design makes the code flexible and maintainable as new vehicle types can be added without changing the core logic of the client code or the factory method. For example, if a new vehicle type like bus were to be added, it would only require extending the vehicle factory class and adding the bus class, while the rest of the system remains unaffected. The factory pattern thus promotes scalability, extensibility, and clean separation between the client and object creation logic. 2. Payment processing system. In a payment gateway application, users can choose from various payment methods like credit card, PayPal, bank transfer, or cryptocurrency. The factory pattern helps by dynamically creating the appropriate payment method object based on the user's selection. This ensures that the payment process is smooth and flexible, allowing the system to easily handle different payment methods without the need for hard-coded logic. If a new payment method is introduced like Apple Pay, the factory can quickly adapt by creating the new payment object, keeping the system extendable and easy to maintain. Why factory pattern? The factory pattern is perfect for a payment processing system because it allows the system to dynamically choose the payment method based on user input. This means that when a user selects PayPal or credit card, the factory creates the corresponding object without altering the core logic. It also makes the system extensible and maintainable by enabling easy addition of new payment methods like Apple Pay without affecting the existing functionality. This way, future updates can be handled smoothly, keeping the system scalable and adaptable. Expanded use case. Imagine a user selecting PayPal as their payment method during checkout. The factory pattern steps in, dynamically creating a PayPal payment object to process the transaction, ensuring the user doesn't need to know how the object is created. This keeps the system flexible and scalable, as it can easily handle adding new payment methods in the future without requiring the user to understand or interact with the object creation logic. It allows for a seamless, adaptable user experience while maintaining clean and maintainable code behind the scenes. Practical implementation. In this example, we implement the factory design pattern to manage different types of payment methods such as credit card payment, PayPal payment, and bank transfer payment. As discussed in earlier responses, the factory pattern centralizes the object creation process, making it easier to dynamically create instances of different classes based on specific inputs. This approach decouples the client code from the specifics of which class is being instantiated, improving flexibility, scalability, and maintainability. The abstract class payment method serves as the base class for all payment types and defines the common interface with the abstract method process in the score pasting. This method must be implemented by all subclasses, ensuring consistency in how payments are processed across different methods. Each subclass, such as credit card payment, PayPal payment, and bank transfer payment, provides its own specific implementation of process underscore payment, which prints the corresponding payment message for the given amount. This setup promotes polymorphism, allowing the program to interact with different types of payment methods through a common interface. The payment factory class contains the static method create underscore payment underscore method, which is responsible for determining which payment method object to create based on the input method underscore type. If the user selects credit underscore card, it returns an instance of credit card payment. Similarly, for PayPal and bank underscore transfer, it returns instances of PayPal payment and bank transfer payment respectively. If the user enters an invalid payment method type, the factory raises a value error to signal that the input is not recognized. This encapsulation of object creation in the factory ensures that client code does not need to know the specifics of how each payment method is instantiated, following the principles of loose coupling. In the main execution block, the program prompts the user to enter the payment type and amount. It uses the factory to dynamically create the appropriate payment method object based on the user's input. This object then processes the payment via the process underscore payment method. The client code remains decoupled from the object creation process, as it interacts only with the abstract payment method interface and the factory handles the specifics of each object to create. This makes the system easily extensible. For example, adding a new payment method, e.g., cryptocurrency payment, would only require implementing a new subclass and updating the factory without changing the core logic of the application. The factory pattern in this example provides a flexible and scalable solution for handling different payment methods, promoting clean and maintainable code by centralizing object creation and using polymorphism to enforce a consistent interface across all payment types. 3. Notification system. In a notification system, users can choose to receive messages through email, sends, or push notifications. Using the factory pattern, the system dynamically creates the right notification sender object based on user preferences or app settings. For example, if a user prefers email, the factory creates an email notification object to send the message. This allows the notification logic to remain flexible and easily extendable, making it simple to add new channels like Slack or WhatsApp without altering the core system. It ensures smooth adaptation to user preferences while keeping the code clean and scalable. Why factory pattern? The factory pattern decouples the notification logic from the main application, making it easy to add new channels like WhatsApp or Discord without changing existing code. This approach keeps the core codebase clean and allows the system to adapt dynamically to different user preferences for notifications. It ensures that the application remains scalable and flexible, accommodating future changes or additional channels without disruption. The factory pattern is key to maintaining adaptability and growth in such notification systems. Expanded use case. If a user prefers receiving notifications through email, the system uses the factory to create an email notification object which handles sending the message. Later, if the user changes their preference to SEMS, the factory dynamically creates an SMS notification object without altering the core logic. This flexibility allows the system to switch between notification channels seamlessly, ensuring that the user's preferences are respected and the notification process remains efficient and adaptable. The factory pattern simplifies adding new channels without modifying existing code, making it easy to manage user preferences. Practical implementation. In this example, we use the factory design pattern to manage the creation of different types of notifications such as email notification, SMS notification, S-Note push notification. As explained in the earlier responses, the factory pattern centralizes the object creation process in a dedicated factory class, making the client code independent of the specifics of which notification type is being instantiated. This results in a flexible, scalable design where different types of notifications can be added or modified without affecting the core logic of the application. The abstract class notification serves as the blueprint for all notification types, defining the common interface send underscore notification. This method is declared as abstract, ensuring that every subclass that inherits from notification must provide its own implementation of how the notification is sent. This use of polymorphism allows the client code to interact with different notification types in a uniform manner, as each subclass provides its own specialized behavior while adhering to the same interface. The concrete classes email notification, SMS notification, and push notification each implement the send underscore notification method to handle sending notifications in their specific way. For example, email notification prints a message indicating that an email is being sent, while SMS notification and push notification handle SIMs and push notifications respectively. This setup encapsulates the details of how each notification type works, ensuring that the client code does not need to be concerned with the internal workings of each notification type. The notification factory class contains the static method get underscore notification, which acts as the factory method responsible for creating instances of the appropriate notification class based on the user's input. If the user selects email, the factory creates an instance of email notification. If SIMS or push is selected, the factory creates SMS notification or push notification respectively. If an invalid input is provided, the factory raises a value error to handle incorrect notification types. This design encapsulates the logic of object creation, allowing the client to simply request the desired notification type without needing to know how the object is constructed. In the main execution block, the user's notification preference user underscore preference is simulated, and the appropriate notification object is created dynamically using the factory. Once the object is created, the send underscore notification method is called to send the notification. This dynamic creation of objects based on user input demonstrates how the factory pattern supports flexibility and ease of extension. For example, if a new type of notification such as in-app notification needs to be added, the factory can easily be updated to include this new type without modifying the core logic of the program. The factory design pattern provides a clean and efficient solution for managing the creation of objects in this notification system. By centralizing the creation logic within the factory, the design promotes loose coupling and makes it easier to maintain and scale the system as new notification types are introduced. This pattern helps ensure that the codebase remains organized, extensible, and easy to modify. 4. Document Management System. In a document management system, different document types like PDF, Word, Excel, and PowerPoint are handled with specific processing logic. Using the factory pattern allows the system to dynamically create the correct document object based on the file type without hard coding conditions. This approach keeps the code flexible and adaptable to new document formats that may be added later. By delegating object creation to a factory class, the system can support a wide range of document types while maintaining clear and concise logic for file processing. Why factory pattern? The factory pattern enables the system to easily incorporate new document types like Google Docs without modifying existing code. This flexibility ensures that the code remains clean and scalable as new formats are introduced. It simplifies maintenance by keeping the object creation logic separate, allowing for smoother updates and extensions when needed. This approach promotes long-term adaptability and reduces the complexity of adding new features to the system. Expanded use case. So, when a user uploads a PDF, the factory automatically creates a PDF document object to manage the file, handling all PDF specific actions behind the scenes. If the user uploads a Word file, the factory instead generates a Word document object, ensuring the system smoothly adapts to different file types without any manual intervention. This makes file handling more dynamic and keeps the underlying logic neatly separated. Practical implementation. In this example, we use the factory design pattern to manage the creation of different types of documents: PDF document, Word document, and Excel document. As explained in the earlier responses, the factory pattern allows the centralization of object creation, making the client code independent of the specific details of how each document type is instantiated. This approach enhances flexibility, scalability, and maintainability by abstracting the object creation process into a single factory class, document factory. The abstract base class document defines a create method, which serves as a common interface that all document types must implement. This ensures that every document type, whether it's a PDF, Word, or Excel document, adheres to a consistent structure and behavior. The concrete classes PDF document, Word document, and Excel document each implement this create method to return a message indicating the creation of their respective document type. For instance, PDF document returns the message creating a PDF document, while Word document and Excel document return similar messages for their types. The document factory class is responsible for deciding which document object to create based on the input document upwork underscore type. The factory method create underscore document uses conditional logic to return an instance of the appropriate document class, either PDF document, Word document, or Excel document. If an unknown document type is passed, the factory raises a value error signaling that the document type is not supported. This design encapsulates the object creation logic within the factory, freeing the client code from needing to know the specifics of how each document type is created. In the main execution block, we simulate different user inputs where the user uploads various document types, PDF, Word, Excel. The factory dynamically generates the appropriate document object based on the doc underscore type input, and the create method is called on the generated object to simulate the creation of the document. This flexibility allows the client code to simply request the document type without being concerned about the specifics of how the objects are created or maintained. The factory pattern in this example provides a clean and modular solution, making the system easily extensible. If a new document type, e.g., PowerPoint document, were to be introduced, the only change required would be adding a new subclass for the document and updating the factory. This results in a system that is scalable and easy to maintain while keeping the object creation process flexible and centralized within the factory. This pattern ensures that the client code is decoupled the specifics of object instantiation, making the system easier to extend as new document types are introduced. 5. Cross-platform game development. In cross-platform game development, different platforms like PC, Xbox, and PlayStation require distinct handling for things like controllers, graphics, and UI. The factory pattern helps by dynamically creating platform-specific objects such as controller, graphics handler, or UI manager based on the platform the game is running on. This allows the game to adapt seamlessly to the unique requirements of each platform without altering the core game logic, making the development process more efficient and flexible across multiple platforms. Why factory pattern? The factory pattern encapsulates platform-specific creation logic, making it simple to adapt to different platforms like PC, Xbox, or PlayStation without changing the core game logic. It ensures scalability by allowing new platforms to be integrated easily just by adding new factory methods. This makes the system flexible and future-proof as it can seamlessly support additional platforms as the game expands. Expanded use case. When the game runs on PlayStation, the factory dynamically creates a PlayStation controller and a PlayStation graphics handler object. This ensures the game handles PlayStation specific input and graphics while the rest of the game logic remains unchanged. It provides a seamless experience across platforms as the factory pattern efficiently manages platform specific differences without altering the core code. Practical implementation. In this example, we implement the factory design pattern to handle the creation of platform-specific objects for controllers and graphics handlers. As discussed in earlier responses, the factory pattern allows us to centralize and simplify object creation, making it flexible and easier to manage. Here we define two base classes, controller and graphics handler, which serve as abstract blueprints for platform-specific implementations. These base classes define the methods, control, and render that must be overridden by concrete subclasses for each platform: PC, PlayStation, Xbox. Each platform-specific subclass, such as the PC controller or PlayStation controller, provides its own implementation of the control method, indicating how input is managed on that platform. Similarly, the platform-specific graphics handler classes provide unique implementations of the render method, describing how graphics are rendered in each platform. For example, PC controller implements controlling with PC keyboard and mouse, while PlayStation controller returns controlling with PlayStation controller. The platform factory class acts as the core of the factory design pattern. It contains two static methods: create underscore controller and create underscore graphics underscore handle, which dynamically generate the appropriate objects based on the input platform, e.g., PC, PlayStation, Xbox. This decouples the client code from the specifics of which platform class needs to be instantiated. The factory method ensures that the correct platform objects are created based on the input without requiring the client to be. If an invalid platform is passed, the factory raises a value error, maintaining robust error handling. In the main execution block, the program simulates the selection of a platform, e.g., PlayStation, and the factory creates the corresponding controller and graphics handler. These objects are then used to call their respective control and render methods, which print platform-specific messages. This setup showcases how the factory pattern centralizes the logic for object creation, promoting flexibility and scalability. If a new platform, e.g., Nintendo, needs to be added, The system can easily accommodate this by adding new subclasses for Nintendo controller and Nintendo graphics handler, and updating the factory without modifying the client code. The factory design pattern enhances the maintainability and scalability of the system as the client code only interacts with the factory, making it easy to extend the application to support additional platforms. By encapsulating platform-specific behavior in the factory and its subclasses, we achieve clean separation between the clean library and object creation logic, reducing complexity and improving code organization. In this video, we explored the factory design pattern and its importance in managing object creation in Python. We covered its core concepts, the benefits of loose coupling, and how it allows for dynamic object creation without modifying core logic. With real-world examples and coding exercises, you now have a solid understanding of how to implement and use the factory pattern to make your code more flexible and maintainable. Thanks for watching, and I hope you found this explanation of the factory design pattern helpful.